Alright, so we're starting on a lecture today on kind of a review of something you might have first heard in elementary school, and that is the description of matter. Now, we have several things we're going to cover on here and get to up to the law of conservation of matter. But the starting here and what matter is, I mean, we really are going back to that old definition we heard of matter is defined as anything that occupies space, and it can be classified as a solid, liquid, or a gas. Now, I know we've heard about fourth state of matter and even fifth state of matter, but in chemistry, it is really just these three. Plasma, which is that fourth state of matter, for us, it really is just gases. So our definition of matter that we're going to use in chemistry is a lot simpler, I guess. All right, so solids, if we think back to what we learned ages ago, solids take up a definite shape and have a definite volume. Now, we got the stacking going on here, but technically in a solid, the positions are stationary, but there is small amounts of vibrations. So the vibrations are basically how a solid absorbs that energy. So the hotter a solid is, the more the vibration is, etc. But they pretty much stay together. They don't move in adjacent to each other. They're just kind of vibrating in place. Liquids will adjust to the volume of their container, but their closeness is about the same as solids. There's really not a lot different. They're just able to freely move around. So if this thing was moving around, you'd see that these molecules don't have to stay next to the one they're near, but they really can't go up and leave that container. They're going to stay at the bottom of it. And then our final one, the movement is fast enough that they actually will take up the entire container's volume. So they have an indefinite volume, indefinite shape. They'll just take up the entire space. And they are moving constantly. And in general, we think of gases moving in nice little straight lines, and the only time they really change is when they bump into each other or the walls. Alright, but if we think back, that is probably the first definition you've heard of matter, and we don't have some of the additional stuff added into there. Alright, so let's see if we can actually figure out some of these things. Solid, liquid, or gas. These are the type of questions I could put on the test, but which one of them has a definite volume but takes up the shape of the container? Well, that'd be a liquid. We'll see these type of questions later on like your practice test and maybe even on the test. So make sure you're familiar with how you can distinguish those and just looking at these previous pages. All right. The weird thing that was on the bottom of that first page, the law of the conservation of matter, it's a neat little physical property or chemical property that we're going to find is true in all cases. Now, later on, we're going to start seeing a lot of reactions, which with nice little arrows, and we're going to see like reactants turning into products. I'm overly simplifying it. But what we're saying in the law of conservation of matter is during that change, the mass will never change. There is no change in the matter itself. It might change phases. It might change how they're put together. But the overall amount would be exactly the same. Now, that can be kind of weird because a reaction could be burning of something. And if I think about burning some wood, theoretically, that turns into carbon dioxide and water. But if you weighed the wood and then at the end of the burning weighed the stuff that was left over, you would definitely see a loss of matter, or at least it would appear to be. All right. Where the law of conservation of matter would correct that is in an experiment like I described, what you'd want to do is seal that wood in a fixed container. Because the oxygen that's in there needs to actually add to that wood as it burns into carbon dioxide and water. And if I could fix that container side, I would actually see that there is no change of mass, and all the atoms are still accounted for. Now, slightly better example to see what we're talking about. I think it fits better nowadays with us all having our cell phones and whatnot. A battery, for instance, now this is like a car battery, doesn't gain mass or lose mass as you use it. Because technically all you're doing is moving electrons from one part of the battery to another part of the battery by leaving the battery itself. But it changes the chemical makeup of the atoms inside there, but it doesn't really change them. They're all still the same thing, they're just connected to each other differently. We could kind of do the same thing if we were looking at how beer is made. So technically the main active ingredient that gives beer its alcohol is there is sugar in there, some kind of carbohydrate to start out the process, and then a yeast will eat on that stuff, and that actually makes the ethanol and technically makes carbon dioxide as it goes in there, so it carbonates that beer. But if we did it in a nice little sealed container, we'd see that the weight of this stays the same through the entire process. We're just changing it. And that is kind of the summary of what the law of conservation of matter says. As you go through a change, a chemical change, we are not going to see a change in the amount of matter. Alright. Enough of that. Our next little section we're looking at is atoms and molecules. Well, it's actually going to be a little bit more. It's even going to be when we start mixing these together. But we're going to start by just distinguishing these things. Now, atoms are the things on the periodic table. And I thought I had the periodic table up here. I don't. I don't know what to do. There's our periodic table. Now, on this is all of the atoms and the elements that we know of in existence. There is 118, that's it. Some of them are far more commonly known than others, and some are ones that you have contact with in your life. Aluminum, for instance, iron, copper, silver, and gold. And that's really the elements. Now, there's not a lot that we find pure, because most of the metals, for instance, they react with the air around us and they oxidize, they rust. And so we actually don't see them in their pure form. We get to see their slightly chemically altered form. Now, on the other side, we have compounds, which is where we combine more than one element in a definite ratio. Now, technically, compounds and molecules are two different definitions, but we've merged them so much in the misuse in the world that they're hard to distinguish anymore. So you're going to see this book actually uses compounds and molecules more interchangeably, and they both kind of mean the same thing here, that there's two or more elements combined in a specific ratio. But I have several things here that we come along with a day-to-day basis that you probably already knew the formula for. Water, H2O, salt, sodium chloride. Might not have known table sugar, but it is just carbons and hydrogens and oxygens. Alright, now something interesting happens when we make compounds from our elements. We drastically change the properties, generally speaking, of what we started with. And sodium chloride's the one I'm going to start with, because everybody knows what salt actually looks like. This is just that standard table salt. Now, if we look at it microscopically, we see that it's just an arrangement of sodiums and chlorines, and they really do kind of look like this picture. Every single sodium is in contact with 6 chlorines, every single chlorine is in contact with 6 sodiums, and nice little ratio that makes these nice little cubes. It translates to what you see when you actually look at a salt crystal up close. They are going to be perfect little cubes, and if you break them apart, they make smaller cubes. But they just make those cubes over and over because that's that general shape of it. And for the most part, sodium chloride is relatively safe. Now, something interesting, melting point here I want to talk about. Sodium chloride is not something that you can easily melt in your house. It won't melt until you get your temperature up to about 800 degrees Celsius. So, really hard to melt that. Now, the reason I brought up that melting point is I'm going to compare it to the its components, sodium and chlorine. Now, chlorine is a gas at room temperature, and it is one that you more than likely have been exposed to, at least in small amounts. Because I believe everybody knows what a pool smells like if it has too much chlorine in it. That smell is the chlorine. Matter of fact, if we had enough chlorine in there that you could see that yellow gas color to it, that's a lot of chlorine. That's almost a dangerous amount. So if it's intense enough that you can see the color, it's very concentrated, and if I had that out and opened the container, we'd all want to leave the room because it'd be burning our eyes. But it's obviously a gas at room temperature, so it boiled long before sodium chloride actually even melts. Now, also on the other side we have sodium. Now, sodium is a metal. If I have a nice little raw sample of it, it looks like a metal. It typically can be shiny, a little bit more dull in most cases. The biggest problem with sodium as a metal, or comparing it to metal, is it will corrode rapidly. As in, this thing looks nice and cut. If that was really in the lab and this was really right out in front of you, you would see it slowly darken up, getting black, and then that black would slowly turn into like a whitish coating. And what you're watching is sodium turning into sodium oxide. And it does it rapidly enough that you can watch it rust. But that's okay if you need it. It's easy enough to cut this. You don't even need a saw or anything. You can actually cut sodium with a butter knife. It's very malleable. Alright, but it's not a useful metal for us in the real world, because it turns out sodium reacts very violently with water. So if you were to make a sample of this and cut out a little spot and you drop it in water, it kind of catches on fire. So let's see. Sodium in water. Here's a neat little video. Now, neat aspect about being able to get a big chunk of sodium is you could indeed throw it out into water and you get something like this. That'd be kind of fun to do, right? Now, technically, in their day, you used to be able to just easily buy sodium. They put a little bit more restrictions on it because we might be too motivated to get some and throw it in our little retention pond in front of the college, and then people get upset. Alright, but it is interesting it does that. Chemically speaking, what's going on is where sodium is at on the periodic table, it very much wants to give off that one electron, because it's on the uppermost, it's that last electron that makes it unstable. And if we lose an electron, sodium suddenly starts to behave more like neon or noble gas, much more stable. So it turns out everything in this first row reacts violently with water, because water will accept that electron really super easy. And actually, as you go down the periodic table, it gets more and more violent. So sodium is relatively safe by comparison to potassium, rubidium, cesium, and, well, francium. Other small problem, sodium has a very low melting point. If I somehow could make a pot out of it and try to boil water in a sodium made pan, so if I somehow stopped it from being able to react with the water, I would find that the sodium would melt before water boils. It melts around 98 degrees. When with water boiling at 100, if I tried to boil water in a sodium pan, it would not. It'd stay a liquid. But I would never get to that, because if I made a pot of sodium and put water in it, it'd just blow up. Fun times. We should actually play around with some sodium more often. All right. When I classify matter, I can classify it in two main categories: pure substance and mixtures. Now, we just talked about the pure substances. They are going to be elements or compounds. And there's nothing in between there. They're either pure by themselves, or they are with other things as compounds. Now, it turns out most of the matter we come in contact fits the category of a mixture a lot more often. Now, even things that we think of pure, like I mentioned salt, and but they have salt water here. But I'd even say table salt would actually fit as a mixture, because table salt here in America typically has been iodized. So that means they've added iodine to it, so it's in our diet. If we're from elsewhere in the world, we might have used sea salt in place of table salt. And that really is different compounds from the ocean. It is a lot of sodium chloride, but it's other things in there. It's what makes that flavor a little bit different. So most things are mixtures. Now, mixtures are going to be split into two different categories. It is really on how they appear, the composition of it. Homogeneous mixtures will look uniform throughout. So salt water is the one that's mixed. Salt water looks just like water generally. Brass is another one listed here. That's just a mixture of copper and zinc as an alloy. And then heterogeneous, non-uniform composition. Now, there are some heterogeneous mixtures I can kind of make look homogeneous. If you think of oil and vinegar salad dressing, if I shake it up very vigorously, it would possibly appear to be a uniform composition, make it look somewhat homogeneous. But everybody knows if you stop shaking oil and vinegar salad dressing, it will separate back out. But that kind of fits here with sand and water. If I stir that well enough, it's just going to look like sandy water. But as soon as it stops movement, we would start to see that separate. So, if it does not stay homogeneous or uniform composition throughout, it is not homogeneous. All right, so I have my mixtures, and what makes it a mixture is the ability to separate things physically. Now, it doesn't mean it's always the same physical process, but they can be separated physically. Now, what I mean by that, if I go back here to my examples, if I have water and sand and I want to separate those, a simple filter will do that, like a coffee filter or something along those lines. The sand would stay on that filter paper and the water would go right through. That'd be an easy physical way to separate them. Now, if I tried that with salt water on the homogeneous side, filter paper won't do it because the salt has been dissolved in the water. But if I were to take that same solution and heat it, put the salt water on in a pot, put it over a fire, I would intentionally boil the water off and leave the salt behind. So that's what it means by physical means, changing the separations by relatively simple processes. Can't do that on compounds. If I try to do any physical separation of just salt, sodium chloride, it stays together because it's that compound. I need to do a chemical change to break those apart. Alright, so homogeneous composition is uniform throughout, heterogeneous composition is not. Now, another thing about a homogeneous mixture, those different parts are not visible. Heterogeneous, they might not be, but they often are easily distinguished. And matter of fact, they'll differ throughout. Like if we go back to that sand and water, it's very possible that you could imagine if we're stirring it up vigorously enough that it kind of looks homogeneous. As soon as you stop stirring it, it's going to be obvious it's not, because you're going to start to see that separation. You're going to see that sand distinguish itself from the water. We're going to be able to tell that that composition varies. Alright, so some examples. So, is pasta and tomato sauce a homogeneous mixture, heterogeneous mixture, element, or compound? Well, unless it's pureed into baby food, that is definitely going to be distinguishable. We would definitely say heterogeneous. Aluminum foil. At least in theory, that is just pure aluminum. So that is an element. Same as helium, just an element. And the air around us, that one might be a bit of a trick question, digging back into the recesses of our brain. But technically, about 70% of the air around us is nitrogen. The rest of it is mostly oxygen. There is a small amount of carbon dioxide and a small amount of water vapor that are detectable at any given time. And I have some others on those. This is the type of thing that might pop up on the test. So research that, make sure you know how to distinguish those. Excuse me. That's just a repeat of something. That's just backing up here to the nice little summary of our types of matter. And our last thing that we're going to cover in this section is temperature conversions. Now, temperature conversions kind of get necessary mainly for body temperature. So, in the medical field, that is. So, 98.6 is what we consider a normal body temperature. But that's in Fahrenheit, and we're going to see very quickly that we are going to start reporting those numbers in Celsius in the scientific world. Alright, so a conversion process is kind of necessary. Alright, but we find that there's different ways of actually measuring this, but we are going to use a thermometer all the time. Now this one here clearly looks like just a standard old style thermometer, had a liquid in there and moved up. But electrical, digital ones are getting far more common. Got the ones you can hold the forehead. But they all technically do the same thing. They're just measuring the vibrations of the molecules they're in contact with, and that translates to an actual temperature. It speeds up the molecules inside the device, and it matches with that measured value. Alright, now, to get an idea of how we do this conversion to convert Celsius to Fahrenheit, I'm going to back up here and talk about the different scales we're actually going to use. So Fahrenheit's the one we're most commonly used to here in the United States. Boiling point of water is at 212, freezing point's at 312, or freezing point's at 32. A difference about 180 degrees Fahrenheit. Celsius, one that you might also be familiar with, boiling point's 100 degrees Celsius and 0 degrees Fahrenheit. Heck of a lot easier to remember than 32 and 212. 0 and 100. That's actually how it was defined. Alright, Kelvin's one you might not be fully aware of. So when we do math on temperature things, there is a need to have a scale that doesn't have negative values. So only thing that Kelvin is basically Celsius scale offset, so there are no negatives. The lowest you can go on the Celsius scale is negative 273. So this is added 273 to it. So this is a very simple little conversion. If I have a temperature in Celsius, I add 273 to it, and that gives me the temperature in Kelvin. Very simple little conversion. Now, we won't need to do that too often, even though Kelvin is that nice absolute scale, and I just said it will help on calculations later on. If we report temperatures at any given moment currently, it's typically Celsius for all things science, and Fahrenheit for all things, I don't know, in the rest of the world, rest of life. But in the medical field, It is kind of interesting that if you were to write in a medical report that someone had a temperature of 98.6, the billing department would probably reject it because 98.6 is up here almost the boiling point of water. So Celsius is that desired structure. All right, the conversion between Celsius and Fahrenheit kind of can be easy. Now, if we jog our memories, you might remember something with a fraction that had 9/5 in it. I think I have a better way to explain what's going on here to distinguish those. So the temperature in Celsius to the difference between the boiling point is 100 degrees compared to 180. If I take that 180 and divide it by 100, I get 1.8. If I multiply that by the temperature in Celsius and then add 32 to it, I would get the temperature in Fahrenheit. That formula a little bit easier to remember and use because we're building it off stuff we see. But those of you taking this class, on the back of the periodic table that I give you on the introduction, I give you both those equations we just wrote down on that page. So don't need to regenerate them; they're provided to you. All right, but we do ask questions, and generally it's actually kind of easy to figure these out because being a multiple choice test, we jump all over the place. So freezing point of water, 0 Fahrenheit, 0 Celsius, or 0 Kelvin. Well, that's just a memory thing, right? And even on something like this, if I said 105.8, which of these is even remotely close? Well, that's definitely way too high. But might not feel comfortable saying 58 versus 41, so when in doubt, that's my Fahrenheit temperature. And we had that nice little equation. The temperature in Fahrenheit is 1.8 times the temperature in Celsius plus 32. So, trusty dusty calculator, I'm going to take 105.8, move this over there, so subtract 32, and then divide by 1.8. So temperature in Celsius is 41. Now my calculator didn't leave that 0. Where this came from, typically a nice little rule of thumb, if you have a single decimal on a Celsius scale, you'll have a single decimal on the Celsius scale. That's typically how we see that done. Alright, I have a few other slides to practice that. Give that a try. You're going to definitely see a problem or two like this on your test. But we're just doing a conversion and we're following that. I don't see that I didn't put one on here that's dealing with just Celsius to Kelvin, but we will have those. There we go. There's one with Kelvin. So 37 degrees Celsius in kelvins. Just remember the only thing that's happening is we're adding 273 to the Celsius temperature. So 73 or 37 plus 273. We get a kelvins of 310. That process kind of a simple little conversion, but you do see that. Alright, and our final thing that we're talking about is changes. We are going to classify all changes in chemistry as either a physical change or a chemical change. Now, physical change, that is really kind of how they're describing like phase changes, going from solid, liquid, or gas, maybe changing size. So a weird one that's a physical change that kind of changes the material permanently would be like tearing a piece of paper. So we typically try to say that the changes, the main difference between these two is that you can't undo a chemical change. But I can't really untear a piece of paper, but we still consider physical change because I'm really only changing the shape. It's still the same stuff. It's still paper. Now, an irreversible change that I could do to paper would be to burn it. Because if I burn it, it turns all black, turns into powder, it turns into, I don't know, trash, I guess, at that point. But that is what we call a chemical change because we're creating new substances. The paper, some of it's turned into carbon dioxide and water when you burned it. So the best strategy to distinguish these two is just ask yourself if it's reversible. If it's definitely an irreversible process, it is a chemical change. There are going to be some times when that non-reversible process is a physical change, but we're talking about changing the shape or size. Tearing paper, breaking tree branches, that type of thing. It's still the same material. It's still be identified as paper. So it's still just a physical change where we just tore it. So some examples that are neat that can add to it. Some of our chemical changes. When I look at this, rushing the nail and tarnishing of a silver. Well, you know how we can get nails that resist rusting? So a nail not rusting is actually a chemical property. It's not a chemical change, but it is a chemical property. Now, as we've understood science, we figured out how to do that with those nails to be a little bit more resistant to rusting. Stainless steel, for instance, very difficult to get it to rust. And all that is just an alloy of iron with the right stuff added that resists that oxidation. Kind of happens the same thing with silver. There are certain things we can do to keep them from tarnishing nearly as easy. But high quality silver typically tarnishes, and so it needs to be cleaned properly. But those are some typical chemical changes, and then the physical changes make a lot more sense when you think about it. Melting of ice, it's still just H2O, different phase. So boiling of it would be the same type of thing. There's that tearing paper, breaking glass, sawing a log in half. Those are those changes that aren't reversible, but they still leave us with the exact same thing. Smaller pieces of glass, smaller pieces of paper, smaller pieces of that log. It's still wood, paper, and glass. And pouring milk. Right? Pouring just seems like we've added a word on there to make you think it changes something. But technically, you pour milk, it's still milk. It's just in a different container. All right, and we will get some of these on that test. So burning a candle, got to be a chemical change. Ice melting on the street, physical change. All right. But you'll definitely see questions like this, and I even have some of these on the worksheet to get you some practice. All right, thank you very much.